Good morning, class. Today we will be looking at question 9. This is from the Metro Central Education District Common Paper, September 2021. So at this point we will be doing the geometry section and the bonus question from this paper 2. Okay. So in question 9.1, we are told that in the diagram below, actually alongside in this case, PMT is a tangent. So if PMT is a tangent, okay, PMT is a tangent, and from here we know that this angle here is equal to that angle there, tan theorem, as well as that angle is equal to that angle. Okay, tan theorem can be applied there. Okay, let's undo that. Then we are told that O is the center of the circle. So if this is the center of the circle, which makes then this your diameter, then angle B or angle L has to be 90 degrees. Why? Angle in semicircle. Okay. This is also the center of the circle, and this being your tangent here, your tangent will be perpendicular to your radius. Okay, so angle C will be 90 degrees as well, radius perpendicular to tangent. Then we are told that MON is a straight line, LNM is 35 degrees. Determine the size of all the angles marked at A to E. Okay, so we must calculate the angles here. Let's make this a bit bigger. So let's start off with angle A. So as we indicated there, that angle A is going to be 35 degrees. So A is equal to 35. The reason is tan chord. Okay, we have 35 degrees. Then we see that angle B has to be 90. So B is equal to 90. Why? Angle in semicircle. Alright. Then we said C is also 90, either tan theorem or radius perpendicular to tangent. Okay, I'm going to go with radius perpendicular to tangent. Okay, my handwriting is not the best of it. Then let's just change the color here, for angle D. Okay, so we can do one of two ways. You can either say angles of in a triangle or angles on a straight line. I'm going with angles on a straight line here. So D is equal to 180 minus 35 degrees minus 90. Okay, and this is straight line. Okay, angles on a straight line. So that's going to give you 180 minus 90 is 90. So it's going to give you an answer of 55 degrees. Okay, it is 55. Then for angle E, we can see, okay, this is a cyclic chord. Okay, and we know that opposite angles of a cyclic chord is supplementary. So E plus 55 is equal to 180. So E is equal to 180 minus 55. Okay, this is opposite angles of cyclic chord, supplementary. So it's going to give you 125 degrees. Okay, let's make this pen a bit thicker. Okay, so let's get the next question. Okay, now we're looking at question 9.2. We are told that in the diagram below, a tangent has been drawn to the circle at B. Okay, so here we have a tangent at B. The diameter DE has been constructed and E joining to C, both with dotted lines, as you can see there. Fill in the missing details to prove that B1, which is this angle here, is equal to angle D, which is the Tanko theorem proof. Okay, so let's look at this here. So we have given you part of the proof, so you just had to fill in the missing statements and reasons here. Okay, so looking at where they started off with, they told us let B1 equal x. Okay, with B1 equal to x, I'll put the x there. So we will answer this in terms of x now. Okay, if B1 is equal to x, what is B2 then equal to? Okay, so you see here, this here is your diameter, this is a tangent, so its diameter stands 90 degrees to tangent. Okay, I don't know is the diameter, what is given there. Okay, so if this angle A and B, the combination thereof, is making an angle of 90 degrees, then B2 has to be 90 minus x. Okay, for those of you who doesn't understand that, so if B1, okay, which is x, plus B2 equals 90 degrees, then angle B2 is equal to 90 degrees minus x. So I took that x over the equal sign. Okay, and what is our reason there? Radius perpendicular to tangent. So that's going to give you 90 degrees minus x. Radius perpendicular to tangent. Okay, so I'm going to fill that in there. 90 minus x. Okay, but we also know that if we look at this here, this is your diameter. Okay, so that means to say that angle C1 and C2 is equal to 90 degrees. Why? So we got angle in semicircle. Okay, so we say angle C1, so that is C1 plus angle C2 equal to 90 degrees. And what's the reason there? Angle in semicircle. Okay, so we have an angle in a semicircle there. Alright, now if you look at this here, in this triangle EBC, we have 90 degrees there, and we have 90 minus x here. So angle E is equal to 180 degrees minus 90 degrees minus 90 degrees minus x. Why a bracket there? Because of the negative. More than one term following a negative sign must go in a bracket. So just multiply that out, it's going to give you 180 minus 90 degrees minus 90 degrees plus x. So 180 minus 90 minus 90 is 0. So angle E is equal to x. Can you see that? And what did I use there? I used sum of triangles. Okay, just take that off. Just write in that. So angle E is going to be x degrees okay, and what is your reason there? Sum of triangles, and it's from triangle ECB or BCE or CEB, doesn't matter the order. Do I have to say this part here? No. Okay. So they will have an x there. But angle E is and angle D is also equal to x. Why? because angles in the same segment. Can you see that? Here's your butterfly, okay? Or for those of the boys, the bow tie. No? So that is angles in the same segment. So angle D is X. We say angle in same segment. And that is coming from arc BC. Do I have to say which arc is coming from? No. Okay? We are nice people. So we can just fill it in there. So it's angles in the same segment and it's coming from arc BC. As I said, you don't have to indicate or state the arc here. And in conclusion, therefore angle B1, as you can see here, let's change the color again, and therefore you see this angle here, it's of course equal to that angle here. Okay, and there's a tan core theorem proven. Okay. Okay, so now we're looking at exercise 9.3. In exercise 9.3, we are told that in the figure, ECG, so ECG, this line here, just get the color there, so ECG and EDF, that line here, are tangents to the circle at A, and the tangents to the circle at center A, with points C and D respectively, which is the points of contact. So if these are tangents, okay, then we know that this angle here, which is C2, is equal to D2, and we know that C2 is equal to D1 and D2 is equal to C1. Tan core theorem there. We also know that that line there is equal to that line there. That is CE is equal to D E, because the tangents from common point or external point there. Okay, which will in turn make that angle equal to that angle. That's the angles in the isosceles triangle, which the theorem that will be used there is sides opposite equal angles. Okay. Then we are told that B is the midpoint of arc DCB. So if this is the midpoint here, we can, and it's marked already that those lengths are equal there. Okay, which now in turn makes that angle be equal to that angle, because angles opposite equal sides. Then we are told that HE, let's go to green here, we are told that HE is parallel to CB, which means to say corresponding angles are equal and alternate angles are equal as well. Okay. Then we are further given that D2, which is E, DB is equal to X. Okay, so we will be using your X in this case. Okay, your variable. So let's take out all this color here. Okay, let's take that out. Okay, so the first question is, write down with reason 5 other angles that are equal to X. Okay, with a reason, we must write down 5 other angles which is equal to X here. Okay, just get our read there. Start with read normally. So if that is X, we see that C1 is X. Okay, this is question 9.3.1. Right here, 9. Okay. So you're saying angle C1 is equal to X, tan core theorem. Okay, my handwriting is bad. Okay, tan chord theorem. Then we said that since CB is equal to BD, D1 is X. Okay, so you say angle D1 is equal to XY. So it will be angles opposite equal sides. Okay, so that's the second angle. Okay, then we say that C32 will also be X, tan chord theorem, with this angle here, D1. So I say C2 is X, tan chord theorem. Okay, so that's the third one. Then we see that the corresponding angles. Okay, so see that that if that angle is equal to that angle. Okay, some learners didn't get this one. So angle H is equal to X. These are your corresponding angles. Okay, corresponding angles with HE parallel to CB. Okay, so that's your X there. People, do not forget to put this in here. Okay, when you use corresponding, alternate or co-interior, you must state the lines that are parallel. Okay, so we need one more. We look here, the alternate angle. So this angle here is C2 and E1. Okay, so angle C2, no, E1, sorry, is equal to X. As we see, these alternate angles there, with HE being parallel to CB. Alright, so there we have 5 angles equal to X. So what I'm going to do is I'm going to take this off. Okay, so that I can keep the diagram in focus. Well, let's first do the next one at the bottom, then we'll take both off. Solutions there, so that we can make space for the next. Okay, so this is going to be 9.3.1 2 9.3.2. so in 9.3.2 we there's 3 there, so I'll have to take this off. Okay. So now we're looking at 9.3.2a. So the question says, prove that DCI is a cyclic quad. Okay, so let us highlight that quickly. DCIE. So this is what they're talking about there. Okay. So to prove something is a cyclic quad, we prove one of 3 properties. We prove that opposite angles are equal. No, opposite angles are supplementary. We prove the converse of angles in the same segment, which we will be using here. Or we prove that the exterior angle is equal to the interior opposite angle. Okay. So let's undo that one. Okay, I just had to realign these things. Yeah. Okay. So as I indicated, to prove that something is a cyclic quad, we prove that opposite angles are equal. Now, opposite angle supplementary, exterior angle is equal to the interior opposite angle, or we prove that the converse of angles in the same segment, the one we will be applying here. So as you can see here, that angle E1 is equal to D1. So we say the angle E1 is equal to angle D1, which is equal to X. That is proven to us. Proven by us, sorry. So we can say therefore CIED is a cyclic quad. Why? Because the converse of angles in the same segment, or equal angles subtended by chord CI. Okay, you can just say equal angle subtended by chord, but it's a chord CI, that is. You don't have to mention the chord's name, or you could have said converse of angles in the same segment. Okay, so now all cyclic quad properties are evident in this quadrilateral here. Okay, then in the next question we are asked to prove that DE is equal to CH. DE is equal to CH. Now we don't go straight into that there, as you can see. There's no link between it, but we know that CH, okay, is equal to CE. Can you see that? And why is that the case? Because of the base angles here equal. Okay, so CH is equal to CE. The reason there is sides opposite equal angles. Sides opposite equal angles. Then CE is equal to DE. And why is CE equal to DE? Because angles tangents from common point. Tangent from external point. Sorry about this handwriting. My handwriting is bad, but not this bad. Okay, but yeah. So what we can say here is that since there is a common, as you can see, a common, it's common length here. So we can conclude therefore CH is equal to DE. And that's what they wanted us to prove. Okay, that CH is equal to DE, or DE is equal to CH, is the same thing. Okay, let's go black. Then in C, the question says you must prove that. I don't think we should. Okay, but anyway, EIH is a tangent. CIH, this length here. EIH is a tangent to circle CIJ at I. Okay, CIJ, no, it's not CIJ. BCI. Okay, so it's BCI. Okay, just take it out. So this angle, this circle here. Okay, so in other words, if this was a tangent, then angle I would have been equal to angle, this angle here, which is CBI. Why? Because the angle, tan chord theorem would have been evident there. Okay, so for us to prove that it is a tangent, we now prove that CBI is equal to angle I1. Okay, we prove the reverse of the tan theorem. Okay, and that's what we call the converse. Okay, let's just take these things off. So if you're looking at this angle here, remember we want to prove this angle and that angle is equal. Okay, but of course you won't go straight into it. So we know that firstly CBI, angle CBI, is equal to, as you can see, exterior angle is equal to sum of two interior opposite. CBI is equal to 2x. Why? Exterior angle of triangle. So exterior angle of triangle is equal to sum of the two interior opposite, and it's a triangle CDB. Okay, so there's 2x here. Alright, let me just take that blotch away and put the 2x. Okay, you can't see it, but it's your 2x there. Now if I can prove that I1 is also equal to 2x, then I've done the job. Then I can link those two angles together. Okay, however I1, you see how we can link this? I1, okay, as you can see, I1 is equal to the combination of C2 and 3. Okay, alternate angles there. But I need an angle for E3. If I can prove E3 is x, I've done the job. Okay, but we have already proved that CIED is a cyclic quad. Okay, so we can say that C3 is equal to D2. Can you see that? Angles in the same segment. So C3 is equal to angle D2, which is equal to x. Okay, so it's angle in same segment, and it's coming from arc IE. Again, you don't have to mention the arc it's coming from. Okay, so there's an x here. Then I1, okay, angle I1, as we said, we're going with alternate angles there. So I1 is equal to 2x. Why? It's alternate angles with HE being parallel to CB. Okay, so there's your 2x there. So I've done the job now. Can you see here? So we say since angle I1 is equal to CBI, which is equal to 2x. Since that is the case, we can conclude therefore AIH is a tangent to circle through PCI at I, and the reason there is the converse of the tan theorem. The converse of the tan theorem, or the proper wording, which is angle between line and chord, equal angle in the alternate segment. Okay, that is the converse of the tan chord theorem. Okay, so if you had a problem with this in the exam that passed, or when you answer this question, okay, and you didn't get your full marks here, pause the video and redo this question. Okay, it's a good question to understand. Okay. Okay, so now we're looking at question 10. The question says determine the value of x, giving a reason for your answer. Okay, so so as you can see, these lines are parallel, so we can use the proportionality theorem. So we say 4. We can say that 4 over x is equal to 3x over 3. Okay, so I say 4 over x is equal to 3x over 3. And your reason here is your proportionality theorem. Okay, so we cross multiply, so it's going to give you 12 is equal to 3x squared divided by 3, so x squared is equal to 4. Square root thereof is going to go plus minus 2, but since x has to be positive, so it's only positive 2. Okay, that was a fairly simple one there. Otherwise I could have said 4. I could have gone with this whole length here. I would have said 4 over 4 plus x is equal to 3x over 3x plus 3. Okay, or I could have said x over 4 is equal to 3 over 3x. Okay, and there's variations that could have done instead of the straightforward way that I've done it here. Okay, let's got the next question. Okay, if I had made any errors, please contact me on that number. Otherwise, if the shorter methods or something I've explained wrong or wrongly, you can contact me on this number. Okay, so we are told that in the diagram the lengths are shown. So we are given a couple of lengths there. Note that BD is 8 centimeters. The question says determine CD to 1 decimal place giving reason. Okay, so we need to calculate CD to 1 decimal place. So if you look at what we have here, now remember the question is for 5 marks. If we look at CD, there's CD. Okay, now some people have used Pythagoras. Okay, I can't understand why, as you can see that it's not a right angle triangle. Okay, so it needed to be a right angle triangle to have applied the theorem of Pythagoras there. Okay, so as you can see here, we can prove similarity first. If we had proven similarity in this two triangles, then we can use the proportionality, the similarity reason that would derive from that proof. Okay, so the two triangles we're going to work in is going to be BFD. So we start off by saying in triangle BFD, okay, and triangle CED. Okay, I'm sure the order is not right at this point. Okay, but for the two triangles, that one there and this big triangle here, we can say that angle D is a common angle, and B1 of course is equal to angle C. Okay, that is going to be exterior angle is equal to the interior opposite, or we can go with F3 is equal to F2 is equal to angle E. Okay, so so let's go with it. We then say angle D is your common angle. Then we say that F2, angle F2 is equal to angle E. F2 is equal to angle E. Why? Because the exterior angle of cyclic chord. Okay, so I can conclude therefore the last angle, which is B2, has to be equal to angle C. Why? So it's a third angle of triangle. Or we can say, could have said exterior angle is equal to the interior opposite of a cyclic quad. Okay, so we can conclude now therefore triangle BFD, yeah, my handwriting, is similar to triangle. So B corresponds with angle C. So I go C. F corresponds with angle E, and D is the common angle. So D corresponds with D, and your answer there is angle, angle, angle. So from here, from the fact that those two triangles are similar, we can go and say, okay, say now that BF over CE is equal to, so BF over CE equals FD over ED equals BD, which is first and the last, over CD. Why? Because your triangle BFD is similar to triangle CED. Okay. So, with that in mind, we're going to investigate where is FB. BF is going to be 3.5 over CE, which is 5, equals FD, which is unknown, ED, unknown, BD is 8 over CD, which is what you want to calculate. Now, did I have to say this here? No, you didn't have to. Okay? Because what we wanted, there is enough information there. So what we do now is we cross multiply. Okay? So it's going to be 3.5 CD is equal to 5 times 8, which is 40. So CD is equal to 40 over 3, 5. Put that in our calculator. Let's get the calculator. So that is simply 40 over 3.5. That gives us 11,42. So remember, the question says to one decimal place is going to be 11,4. Okay, that's going to be 11,4 centimeters. Okay. Okay, so for this question, I think this is the last question before the bonus question. People, there's more than one way of doing things, okay? So, the way I just do it is the way that, or the way I'm doing it in the videos is the way that pops up in my head at the time. Okay, or the way that I think, okay? There are times where there's another way which is even shorter than the way I'm doing it. You can adopt that way, no problem. Okay, as long as it's mathematically correct. Okay, the question says refer to the diagram. We are told that A, B, C, E is a parallelogram. So if this is a parallelogram, all parallelogram properties are evident here. As opposite angles are equal, two pairs of opposite angles are equal, two pairs of opposite sides are equal, two pairs of opposite sides are parallel, and diagonals bisect each other, which we will be using in this diagram here. Okay, with diagonals BE and CA, which now means to say that that length is equal to that length, and this length there is equal to that length there. Okay, then we are told that BF, yes, it's BF, is parallel, BF, not BF, FD is parallel to D, GB. So FD is parallel to FB, which now means to say, which I can apply, is that if C is equal to FC over FG is equal to CD over DB. Okay, and that's your proportionality theorem rule there. Okay, then we are told that AG is 72. So if AG is 72 centimeters or units, then this has to also be 72, right? As we see, the diagonals bisect each other. Okay, then we are told that we are given a ratio that BD is going to be 3 and DC is 5. So we say that it's going to be 3K and that's going to be 5K. You could have said A or B, whatever. Okay, but we can't just say 3 and 5 because why? It is not length, it's a ratio. Okay, so the first question says, give the reason the length of CG. So I indicated earlier on that CG is going to be 72 units. Why? Because the diagonals bisect each other. Okay, so in 10.3.1. So we're saying that CG is 72 degrees. 72 degrees. Why? Because the diagonals bisect each other in a parallelogram. Okay, so the diagonals bisect each other in a parallelogram. In 10.3.2, the question says you must calculate the length of CF, okay, which is this length here. So we know that CF over CG is equal to CD over, so since I went with the whole length of CG, you must go with the whole length of CB. Make sense? So CF over CG is equal to CD over CB. Or I could have said CG over FC is equal to CB over CD. But we won't say CF over FG. Why? Because then there's two unknowns. It's FC and GF. Okay? Since we got the length there of CG, that's why I'm going with the whole length. Okay? So I hope that makes sense. Again, that CF over CG is equal to CD over the whole length here. And we can get the whole length here, which is now 8K. Okay? And my reason here is the proportionality theorem. Okay? The theorem with FD being parallel to GB. Okay, so CF is what I'm calculating over 72 units equals CD, which is 5K, over the length of CB, which is 5 plus 3, which is 8K. Of course, the K's cancel. So CF is equal to 5 times 72 over 8. We can cross multiply. It's going to give you CF, 8CF is equal to 5 times 72 and then divided by 8. Okay, so that gives us, just put here, 5 times 72 divided by 8 gives you 45. That's going to give you 45 units. Okay. Then, just pause this. Then in the last question in 10, let's change our color here. In question 10.3.3, so remember now this is 45 here. No? Okay, because I'm going to take this now off. Oops. Okay. So in question 10.3.3, it's a ratio question. We must calculate the area of triangle FCD over the area of triangle ACB. Okay. So just take this out here. You can see I'm still very slow with these things. Alright. So if you're looking at triangle FCD, this triangle here, over triangle ACB, which is that whole triangle there. One thing we know is that it has a common angle C here. So of course I can go with the area rule, because we have two lengths and included angle. So it's definitely the area rule, since angle C is also your common angle there. So if I apply the area rule there, it will be a half CF, which is 45 degrees. Okay, just put the CF, times CD, sine of angle C, over half CA times CB, sine of angle C, which is your common angle there. Okay, so what's going to happen here is that, of course, we could have write it in the next step again, but we can cancel it out at this point already. Okay, so CF's length is 45. Okay, 45 times CD, which is 5K, over CA. Remember now that is 72 and that is 72. So it's 72 times 2, or we could have written 144, I think it's 144, times CB, and CB is going to be 8K again. Okay, so what happens now is that the K's cancel. Okay, and then we can put the calculator. So put it in the calculator, it will be 45, 144 times 5 times 8. So it's going to be 25 over 128. There's 25 over 128. Okay, or you could have written it as in decimal, but as you can see, it's a ratio given there. Again, if I had made any mistakes, please contact me on that number. Okay, well, there's an easier way, of course, as well. Okay, and now we take us to the bonus question. Let's cut that quickly. Okay, so in question 11, the bonus question, we are told that in the diagram shows two tangential circles with the centers on the x-axis. These circles fit within the largest circle defined by x squared plus y squared equal to 144. So the big circle's equation is this here. Okay. So in other words, remember the center can be drawn from here, which is at 0 and 0. We know that. And this here tells us r squared, which means to say the radius of the circle is going to be 12. So from there to there is going to be 12 units. Okay, as shown, if the radius of the smaller circle is half the radius of the middle-sized circle, so if this diameter, you see, if the radius is half of this circle compared to that circle, then the diameter of the circle, if I call that x, to the diameter of the circle is going to be 2x. Or if you let your radius be x, then that's going to be 2x and that's going to be 4x. Okay. If the radius of the smaller circle is half the radius of the middle-sized circle, find the equation of the smaller circle, or the smaller circle. So in other words, I need to know the center of that circle, okay, and I need to know the radius of that circle. Alright, so if this is going to be x and for the other circle is going to be 2x, then the sum of the two, x plus 2x, has to be equal to 12. So that length is given as 12. So 3x is equal to 12, so x is simply 4. So the diameter, let's just take a write that 4 meter. So the diameter of this circle here, of course, is 4. So what is the radius of the smaller circle? It has to be 2. Okay, the radius of the big circle is 12. The radius of the small circle is 2. So if that is going to be 2, okay, then from the point 0 till the center of that circle is going to have to be 10. Why? Because at this part is 2, that is 2, which is 4, and that is 8 here, as you can see here. Okay, so 8 plus 4 is 10. So the C value, or not the C value, but the center of the circle on your X, your A value, is simply 10. So the center is going to be 10 and your Y value is 0 since on your X axis. And we have a radius of 2 as indicated there. So we got X minus A squared plus Y minus B squared is equal to R squared. So it will be simply ax minus 10 squared plus y minus 0 squared, which is y squared, is equal to 2 squared, which is 4. Okay, that's the equation of the circle, then the smaller circle. Okay, good luck with your final exam. Okay, all the best.